going to sing you a little intro. I'm going to sing everyone a little intro. This is the backstory of the MLOps community. I should have wrote down lyrics, but I'm just going to improvise it as we go. You can hear the guitar all right?
Yeah, it sounds good.
Last year, the end of April, Luke said to me, "Hey man, you might want to sit down and grab yourself a beer. What I'm about to tell you is not gonna be so easy to hear, On Friday, you don't have a job. We're gonna have to shut down this MLOps company. Whoa, COVID has taken another victim. Oh, this time it's us, but the beauty of this was that Luke decided to start a community right before we went under. And then I took it and I went, hey, let's interview a bunch of people. So I'll give credit where credit is due. This community belongs just as much to me as it does to you. Luke was the first guest we ever had on the Meetup. And he said, so much the YouTube comments ate him alive. I've heard it's gotten better and he decided to get a speaking coach. So now we're not gonna have any problems today. Luke, I'm gonna hand it off to you. This is your time to shine. Thank you, Luke, for joining us today. It's such a pleasure to have you here in so many different ways. And although you ended up having to fire me a year ago, I'm so happy that we had a moment to work together because you were the best boss ever. And that, my friends, is the intro for Luke Marsden, who is the founder and idea man behind this community. So if you have enjoyed any of the meetups or coffee sessions at all over the past year and a half, you can thank him.
Wow, that was incredible. Thank you, D.
You thought, let's just tell everybody, just so you all know, he was gonna try and put some funny words in his bio so that when I sang it, it would sound all weird. But I told him, no, you get a special intro. You don't get just the bio singing that I normally do. You get something spot on that is a little closer to home. Anyway, go ahead, share. I think everybody's here for now, or at least most people have showed up and they're probably sick of hearing me sing, but that's what you got to deal with.
Thanks, Demetrios. That was amazing. Yeah, and I mean, most of the, like 99% of the credit for the community goes to you and your incredible hard work, both at the end of that MLOps company you mentioned and in the time after that. So thank you. Cool. So I guess I'll just jump in. I want to encourage people to ask questions throughout this because if I really want to bring everyone along with me on the journey through this content that I've got here. So if people are confused or if you've got questions, please drop them in the chat. And we can address them as we go. So, yeah, I'm going to talk about building machine learning models into Docker images. It's sounds like potentially a simple topic, but it actually has some complexity that's quite interesting. So I'll start by talking about kind of the simple case, and then talk about some of the trade-offs and some of the aspects of the kind of social aspects of getting machine learning models built into Docker images in a company where there's maybe a machine learning team and a DevOps team, and looking at how the ML team and the DevOps team can collaborate as well as possible. So yeah, what I'm going to talk about is just start with the simple stuff, like what is a machine learning model, or what is Docker? Why would you want to build a machine learning model into a Docker image? And then I'm going to do, I saw on the community Slack that people really like live coding. So I'm going to try and do as much live coding as I can / demos. So wish me luck. I don't have backups for most of the demo videos, so please pray to the demo gods for me. So we're going to do the first demo will just be a simple Docker build of a model, and then sending a request to it so we can do inference. I'm then going to talk a little bit about this question of to bake or not to bake. That's the question in particular. What do I mean by baking models into container images, and why is that even a question? And then we're going to look at this, and then we're going to do a demo which shows how baking can go wrong, or rather, sorry, that not baking can go wrong. So the opposite of baking is downloading, and I'll explain that in more detail, but I'll show a demo of how that can fail spectacularly, and thereby kind of show my bias on the answer to that question. Then we're going to look at some security issues around building containers inside containers. And then I'm going to share a demo of some technology that I've been working on with the Modsy team that's called Chassis. And we're going to look at how, which is fully open source, and DevOps teams are very welcome to take it and build on top of it if it's helpful for them, that will automate baking containers from machine learning models in Kubernetes and deploy them to KFServing. Then I'm also going to talk about the open model concept, which is this idea that why not build container images that can run in more than one place? Because if you do that, then you can avoid lock-in. And then I'm going to give a quick demo of deploying the same model that we built in step 3 to a different platform, in this case, the Modsy platform. And then there's just a piece I want to finish on around how DevOps and ML teams can collaborate best, and what can we do to help DevOps and ML teams collaborate better, because ultimately what everyone is trying to do is to ship models into production quickly and safely, and create business value from ML. And if you can't get models into production quickly and safely, then it's very difficult to do that. So yeah, that's what I'm going to try and do today. And yeah, any questions, please hit me up as we go through. So let's start by just talking about the basics. So what is a machine learning model, and what is Docker and a Docker container? Probably most people in the room know what a machine learning model is, but I'll just give a very kind of simple description of that. So a machine learning model is really a piece of data, which is the set of weights that are associated with some neural network or other parameters in general. It's not just neural networks, but any machine learning model will have parameters that, those parameters are kind of how the model gets trained. And in the case of a neural network, every neuron in the structure of the network is kind of fixed, but then it learns during the training phase what the certain weights are. And so the weights are a way to take a given network architecture and specialize it so that it's been exposed to some data and it's learned from that data. And so the actual machine learning model, kind of from the computer's perspective, is a file or a set of files that have these weights in them, that together with the network architecture can be used to actually run the model and kind of start it up again, and then send more data to it to predict the outcome. So yeah, it's these weights files plus files that describe the actual structure of the network or the model. So it's a bunch of files on disk, basically, and it represents kind of the trained model. And then, okay, so that's a machine learning model. Well, what's a Docker container? Well, Docker is a tool that helps people to capture the state of, effectively the state of a running Linux system. So if you have a computer running Linux, then you can install a server on it, like a web server or an API server that has a machine learning model behind it or something like that. And you can expose that server on a port, for example. But what Docker does is it allows you to create like lots of little read-only Linux systems. So it allows you to kind of reproduce it allows you to reproduce a running thing both on your laptop when you're developing it or in development, and then ship exactly the same thing to production and know that it's exactly the same thing is going to run when you get to production. And so Docker has taken off and become very popular because it helps to solve the problem that otherwise you might have to manually manage a bunch of servers and manually install dependencies on those servers and so on. And so it's become kind of almost a de facto way of building and shipping and running machine learning models and the servers that serve them by kind of packaging them up into Docker containers. And so what this thing here is, the kind of the blue layers in this diagram are how Docker images get made up. So when you're creating a Docker image, you start with the base layer, and it's kind of everything is sitting on top of the kernel. And you can think of Docker containers like lightweight virtual machines, where all the containers share the same kernel rather than having an individual kernel per VM. That's not necessarily a helpful way to think about it if you're not familiar with virtualization. But anyway, you've got this kind of shared kernel layer, but then you've got this base layer, which could be something like a Debian or Ubuntu base image. And then you've got these multiple layers that you build up on top of it. And so the example I'm giving here is that we add a model server, so something like TensorFlow serving or a Flask Python server that's going to respond with certain inferences when it's given certain inputs. And then you can also bake the model weights, so the actual files that make up the weights of these neurons or whatever the type of model is, and the model architecture itself. Just add those files to the Docker image, and then you've got this kind of shippable unit that you can move around. You can push it to a container registry, and then you can run that thing in production or in development and kind of move it around all over the place. So it's a nice way of packaging the machine learning model, which makes sense from a data scientist's machine learning perspective, along with all of the dependencies that it needs to run in exactly the same way wherever you run it. So you won't have the problem that when you actually try and run the model in production, you've got the wrong version of OpenCV installed on the server or something, and it won't work, or it'll behave weirdly in a way that's difficult to fix. So yeah, I promised lots of live coding. So let's try and build a model into a container and send a request to it. I'm going to do that here using this test drive system, which gives me access to a little Linux virtual machine that's got a bunch of stuff installed on it. And what we're going to do...
Can you make it bigger?
Yeah, sure.
Bigger. There we go.
Is that okay?
Yeah, yeah, I think so.
If I make it too big, then I won't be able to see it with my eyes.
That's good.
Or I won't be able to see everything I need to see. Okay. So cool. So basically what I've got here is Just need to install Vim. So yeah, basically what I've got here is a very simple app, which, and this is like the super simplest way that you could serve a machine learning model, just by having a Flask app written in Python that is an HTTP server, like a REST server, that opens a model file when it starts up, and then it calls model.predict with some post data whenever it receives a post on Slash. And so that's fine. The other thing, though, is that we need the actual model file itself, so that model.pickle file, and that one is here. So I pre-trained this model. I won't go into all the details about exactly how it was trained. It's just a scikit-learn model that was trained quite simply. I think it's trained on the diabetes data set. So I think it tries to predict whether you have diabetes or not. And then I also need, and I promised you live coding, because this Docker file that we have here isn't actually quite right. But let me see. Resizing the window kind of screwed things up, so I'm going to try a different way of zooming in. How about that? So what we can see here is this is a version of a container. So let me just describe kind of what we're looking at. We've actually got yeah. So this is a Docker file. And so if you're not familiar with Docker files are basically a list of instructions that tell Docker, when it's building one of these images, what to put in those base layers. So if we go and look at kind of this picture here, each line in this file basically puts a new layer on top of this container as you're building it up. And so if we go back over here, then we can see from Python 3.9 is the base image that this thing is being built from. Then it sets, Workter says, run everything inside /app inside this container. So kind of make that the working directory. And then these copy commands are pretty self-explanatory. It's like, let's copy the requirements.txt file that we have here into the container image. Then we run pip install on the requirements.txt, and then we copy the code that we want to run in, which is this serving code that I showed you. But what we haven't done yet in this image is to actually copy the model in. So let's do that. The special lines that we need are here. So that's basically two more layers that we're adding. So we're adding this histogram file. Don't worry about what that is. The main event here is that we're adding the model.pickle file, and we're putting that in /app/model.pickle, and that's where it's going to get looked for. And then we can just build the container image. So Docker build -t takes the name of a tag, which is kind of the name that you give to the image. And then dot just means use the current context. So the current directory that you're in to build the container image. Or for things like when you have this copy directive, the dot just means copy things basically from the current working directory. So we see we've got this model.pickle file here. So we built a container image, and now we can run that container image. And that's now running in the background. And I can now send a request to that container. And so I've sent in some features to predict whether or not I'm likely to have diabetes, I guess. And the model server responded with a result, which is 106. I don't actually know if 106 is a good score or a bad score for this model, but that shows that it's working. So that's kind of like the basic, the easiest way that you could build a container image or build a machine learning model into a container image. And that basically that would be to learn how to use Docker, to figure out how to run your model in production. So to provide some code like this serve.py file that responds to HTTP requests, and then to create that container image yourself. And then I guess run it in a Kubernetes cluster or ask a DevOps person to run it for you or something like that. So yeah, any questions about this kind of base, no pun intended, base layer of understanding around what we're doing with machine learning models and how we're baking them into, or how we can put them in container images?
The chat is pretty quiet at the moment.
Cool.
But feel free, if anyone has a question also along the way, I can stop Luke if you just post it in, and then we'll have him answer it. Oh, here we go. We got one. Right on. Okay. Do you containerize for batch predict too?
Yeah, you absolutely can, yes. So this is an example of a REST interface. Actually the platform that I'm going to show this integrating with later, this platform called Modsy, is kind of a batch platform. So you can upload a large chunk of data to it and it will chunk through it and give you the answers. And the way that that's implemented is that each kind of component of a batch gets sent to the containerized model that's containerized in much the same way. So yeah, you can take the same approach and run your batch operation through just effectively sending multiple API requests. So yeah, the Modsy is a good example of how you can do batch prediction with containerized models. And I've seen that be used elsewhere as well. So I hope that answers the question.
Sweet.
Cool.
I'll let you know if anybody else has one. Thank you.
So to bake or not to bake, I want to talk a little bit about the pros and cons for baking, but first I'll describe what the heck do I mean by that. So what we just saw was taking these model weights and actually baking them into the container. So there's a layer here that has this model weights files inside the container itself. Now, there's an alternative to this, which is somewhat popular. I think it's kind of about 50-50 in the community as to whether people are baking versus downloading. The alternative is to have the model server, when it starts up, download the model weights from somewhere, specified by an environment variable when the model server starts up. Now, for example, you could write a piece of code in your model server that says, go and download my model at startup from an MLflow server based on an environment variable that I specify. Now, that's actually has some complexity because what you're doing there is you're adding your MLflow server to kind of the surface area of the infrastructure that has to be running in order for your model to be running. So basically there's like an operational challenge there, is that if you go for this downloading approach, then wherever you download your model from, it has to be online at the point at which your model starts up in order for everything not to break. So that's kind of one of the challenges with that. And I'll demonstrate that in a moment. I guess another challenge is, but on the other hand, the benefit of not baking your models into your container images is that you'll just end up with far fewer container images, because you can have like a generic container image that knows how to run a PyTorch model or something like that, as long as it has the right dependencies in it. And then you can reuse that with multiple versions of the same model, for example, just by changing that environment variable, which is kind of where it downloads the model from. Now, there's another worry around not baking, which I have, which is that if you don't bake your, I've seen a lot of people basically put their models, just throw their models on S3. That seems to be quite a common pattern, which is you put the model weight files on S3, and then you deploy your model servers that download the models when they start up. Everyone's happy. Then your deploy to production step can be that some person on their laptop uploads a new version of the model file to S3, and then you restart all of your containers. Now, that has alarm bells going off all over the place for me, because you are basically changing which version of the software is running in production, but not recording which version was running at any one time. And so there's when people take that approach, I feel like then you're really asking for trouble. So I'll talk about that a little bit more later on, but yeah, I think, I mean, you can kind of tell, like, I'm biased towards towards baking being best.
Well, I love that, how you're framing it too, and saying like, you're setting yourself up for disaster there when you do it like that. And yes, I mean, there is a reason. I mean, what I really love about your background and your knowledge is you have all this DevOps best practices just like in your blood, right? Mm-hmm. So when there are things that come up in MLOps, you instinctively know, like, that could be a way to, that's a recipe for disaster right there. So,
frankly, yeah.
We've got a few questions coming through that I want to ask you before we jump into the demo. Durga's asking, what's the best practice or design to follow when API serving should have fewer latencies? For example, if prediction response should be less than 10 milliseconds.
Yeah, so the first thing that comes to mind is just making sure that you're not doing anything like loading the model every time you process a request. So the model server should load the model and initialize it if it needs to be initialized when the server starts up, and then make sure that it doesn't try and initialize or load the model every time it responds to a request, but just reuse that cached model object to send requests to. Another aspect to this is, well, you can only go as fast as the model itself. So there's kind of the stuff around the model, but then like the model server, but there's the model itself. And if the model itself is just slower than 10 milliseconds at processing a certain type of data, then there's nothing you can do about that. Apart from, well, so firstly, you need to make sure, so you should benchmark your models when you're developing them to check whether they can actually meet your kind of production SLA. And then the other thing would be that you probably can speed your models up in production if you need to, but that might be a matter of running them on GPUs in production and stuff like that. So then, yeah, making sure that you've got access to the right compute and configuring your CUDA drivers and stuff, which is a whole other talk. Then the other piece that comes to mind is making sure that you can deal with parallelism. So oftentimes a Python server might be kind of a naive implementation of a Python server would only be able to process one request at a time. And so you might find that your response latency is fine when your service is quiet, but it goes through the roof, and you get horrendous tail latencies when you have concurrency, you have lots of requests at the same time. And so there's a couple of ways of dealing with that. In Python, you can do multiprocessing. I mean, that's basically what fast CGI was designed to solve back in the day, and there's a bunch of different approaches around that. So yeah, just making sure that you can deal with parallelism or multiprocessing, which can be harder when you've got GPUs because you might not be able to use them in parallel if you run out of memory and stuff. So yeah, those are the topics that come to mind around that. I hope that helps.
Sweet. So another question coming through. I noticed that you have several copy directives in the Docker file. Is it possible to combine them to reduce the number of layers in the image and thus the image size?
Yes. So I think there's like a secret feature in the Docker file format, which is that I forget if it's copy or add. I think it's add, and it's not the other one, which is confusing. But if you add a tarball, then it adds the contents of the tarball to the image rather than the tarball itself, which is like a bit of a weird feature because it's really implicit and a little bit surprising. And I think that's why they implemented copy, because copy doesn't have that weird behavior. But you can use that behavior to add multiple files in one go if you want to. And similarly, if you're using the run command, then you can chain your run commands with lots of ampersand, backslashes, which you'll see all over the place in Docker images, in Docker files to reduce the number of layers.
Nice. So last one before we move on. Eddie's asking, can you discuss more on your views on the trade-offs of to bake or not to bake question in the context of model updating rollbacks for continuous learning? On a related note, are there tools you use to manage the timeline of swapping production models?
Yeah, definitely. So I think in terms of model updating, it's a really good point. I think that when you're doing updates and rollbacks, that's when you really, really want to bake, because if you've got like two different sources of truth for what version of the software was running in production, i.e. you've got the tuple that is both the Docker image that you used and the model files that you had on your S3 server or whatever, then actually knowing that you've updated the right thing, or that if something goes wrong, that you've rolled back the right thing, and that you'll make sure that you're keeping a record of both of those things rather than just the one of them, is just going to make it harder to keep track. And so there's fewer moving parts when you're baking something, and you don't have this problem of like, oh, am I running the right version? If I need to update the model server, am I running the right version of the model server with the right version of the model, and so on. So yeah, definitely in terms of rollbacks, it's rollbacks and updates. That's where baking helps you be more confident that, for example, if something goes wrong, then you've rolled back both the version of the libraries and the version of the model to the previous known good version, rather than like maybe in a panic, like rolling back the model file, but not the version of the server, and then everything might be down. So like that's I think that definitely skews towards baking, making it easier from an operational perspective. In terms of managing the timeline of swapping out production models, there's a whole space of tools around continuous delivery. And so if you Google continuous delivery tools, then you'll get a bunch of them. My favorite approach is called GitOps. And there's tools like Flux and from Weaveworks and Argo CD, which allow you to use a Git repository as a source of truth for what should be running in production. And then it's like Flux's or Argo CD's responsibility to reconcile your cluster to the state of truth that you're asking for in the in your version controlled YAML or whatever. So definitely look into continuous delivery tools, and there's a whole space of like A/B testing and rollouts and stuff around that, which I probably don't have time to go into.
For another day.
Yeah.
So
Cool.
I guess, let's keep moving. I posted a demo link in the chat if anybody wants to follow along.
Cool. Yeah. And to be clear, there's a couple of different demos that test drives that I'm using. There's the Boxkite one, which is a different system that kind of shows the non-baked approach, which we'll talk about in a minute. And then there's also this chassis.ml link. So if you want to try out the test drive for the piece that I'll show you later, then it's on chassis.ml. So yeah, please post that link as well. So yeah, I'm actually conscious that I'm probably going to run out of time if I don't speed up a bit. So let me show you two more quick demos. So this one, I want to show you the weakness of not baking your models. And I was going to try not to be too biased about this baking versus non-baking thing, but I think it's pretty clear that I am very biased.
Too late.
It's like, don't download your models at startup. It's a bad idea. So yeah, let me show you this piece. So I'm gonna let me just find the instructions here because it'll help me stay on the right track. So yeah, this is a kubeflow MLflow setup that I'm going to show you quickly, and I have to use the right thing. Okay, so here. So I'm just going to spin up so lots of people these days do data science work in an environment like this, which is inside a Kubernetes cluster with something like Kubeflow. And in this case, we're using Kubeflow notebooks. So let's see. I'm going to just spin up a quick Kubeflow notebook server, which is a Jupyter server. I'm going to use this custom image. I'm going to turn off persistent storage for reasons I won't go into, and then configure it to talk to MLflow. And then I can hit launch. And then we can run through this notebook. So this is an example of a system which downloads models from MLflow when it starts up. And I'll actually show you the code quickly for that. The Boxkite project, by the way, is actually about model monitoring, but I'm just using its example because it happens to download models from MLflow at startup. So if we look in this app here, oops, I need to go into the Kubeflow MLflow one. Yeah. So this is going to load the model from MLflow. So actually, when you can see this is a model import time. So model import time in the serve completed file, which gets run when the container starts up. It's actually importing the MLflow client. And then based on this run ID, which is specified as an environment variable, it's going to download from MLflow into this like temporary directory when it starts up, and then start serving the model. So this is like doing the bad thing that I said you shouldn't do, basically. So we're going to train the model. We're going to log it into MLflow. We're going to check that we can send stuff to it. And then we're going to deploy that model into the Kubernetes cluster using some YAML. That the key point here is that we're passing the MLflow run ID from the model that we just trained in the notebook into the production instance of the model that's running. And then we're going to see if it's running. And then we can see, yeah, okay, we can make predictions. So it looks fine, right? It looks like it works, except that if the MLflow server were to were to go away, like nice MLflow server, shame if something happens to it. If the MLflow server were to disappear, then everything would look like it was still working until like Kubernetes automatically scaled up your deployment because you got a spike in load, or one of your servers failed and Kubernetes had to redeploy the containers onto a different machine. And then they would just be silently failing. They would be failing to download things from the MLflow server at startup. So let me try and convince you that this is a bad idea by, I'm going to go in and actually break the MLflow server, and then we can see what happens. I like breaking things. So let's see.
Oh, I love this.
So here's our ML deployment, happily running, la, 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 this is all fine. And then MLflow, oh, looks like you've got a MySQL server, MLflow. Nice database you've got there. It'd be a shame if something happened to it.
That's some serious foreshadowing.
What?
That's some amazing foreshadowing.
So maybe a sysadmin accidentally deleted your MySQL database, or something else bad happened. Like MySQL databases are kind of fragile, right? You don't want to have a MySQL database at the heart of your production system unless you're taking a lot of care to look after it. And the point there is that yeah, like as soon as you use this approach to baking, to downloading your model when you start up your container image, then you're putting all of the MLflow or whatever you're using for model management into your into the production, into the scope of the production system that from a DevOps operational perspective that you have to manage. So let's log out of this MySQL server now and have a quick look at these container images. So as I said, they're still running because they only download from MLflow when they start up. But if we delete the pods, then Kubernetes is going to restart them because Kubernetes is good like that. It's going to try and keep the system up and running. But I delete all three of them.
Can you make it a little bit bigger?
Yeah, sorry. Oh, I think so. No, I can't because when I try and...
Oh, you're already... Oh, okay. No worries.
Yeah. Oh, no, there we go. That's okay. Yeah. So... Yeah, basically we're in a world of hurt now because these containers, when they start back up, they go into error states. And let's see, did I break it enough that it's definitely stopped working? Yep. Okay. So now your ML model in production is down. And the scary thing about this is that it happens sometime after we had the problem with the database. So it's not even going to be easy to figure out like what happened because it was only when Kubernetes started restarting these services. So basically, this is just a warning. Like if you're going to not bake your models in and download them when you start them up, then you have to be really careful to not mess up immutability and reproducibility in terms of just like uploading a new version of the model on top of the old one and restarting things as a way of upgrading them, which is bad. But you also need to start to operate your MLflow or whatever you're using for model management like it's part of your production system, and it kind of brings that into the production sphere.
Well, wouldn't, because I mean, you have Prometheus and Grafana as part of this, right? Like, wouldn't that have caught it?
Oh, yeah. I mean, you can set up monitoring but for your production system, and you should. But you're still going to have to like go in and do something about it. It's still like, it's even more operational overhead to say, okay, well, I have to set up monitoring for my MLflow instances. One of the problems is that MLflow instances are often just set up by the ML team, and they run kind of for the internal purposes of the ML team. And so if they're not centrally managed by a DevOps team, then DevOps might not want to introduce a dependency on them for production. Yeah, so like benefits of baking, model management doesn't become part of your production system. You can still serve inference even if someone's messing with your MLflow instance. There's fewer moving parts and higher reliability, basically. That should have been like that, sorry. When you're doing the downloading approach, there's no guaranteed reproducibility of inference results. You do, however, get fewer overall container images. Like if you have like n different models and m different, if you have m different models and n different kind of model servers or model server versions, then you end up with just n container images rather than n times m. So it's like takes a quadratic thing down to a linear thing, which is good, but it's actually not really a problem to have lots of container images because container registries are built to be able to deal with them, and they're just backed on object storage. Another benefit of downloading at startup is that there's less data. If you've got very large models, like models that are gigabytes big, then you don't have to put those in your container registry. But then you have to put them somewhere else. Like you have to put them in MLflow, and MLflow is backed on object storage as well. So it's all just object storage at the end of the day. And container registries can cope with large container images. So yeah, I think baking models is better. Hopefully I've convinced you. So I then want to talk, and I know that we're actually getting close to the end of the hour. So we've got kind of 10 minutes left. I'll go quickly through the rest, and then maybe we can go 5 minutes over if that's okay.
Yeah, that's fine with me.
So I wanted to talk about the security challenges of building a container inside a container. So this talk wouldn't be complete without a meme. So here you go, here, have a meme. One does not simply build a container inside a container. What I mean by that is that, so for example, what we saw just there was the working environment for a data scientist was this Jupyter notebook that's running inside a Kubernetes cluster, because this Jupyter notebook is running inside Kubeflow notebooks. And so, I mean, I can try, like, how's that? I don't have Docker installed. Docker doesn't run nicely inside a container. And because you're using Kubeflow notebooks here inside Kubernetes, it doesn't work very well if you try and layer things like that. So basically, yeah, like data scientists are often doing work inside a Kubernetes pod these days, even if they don't know it. Or you might be part of a team that's working on building an internal MLOps platform, and you need to have a reliable way to solve model builds at scale. It's generally a bad idea for data scientists to do anything on their local machines. If you have workflows that involve like Alice or Bob, the data scientist, actually building the container images like I showed you in the first demo, just on their own machine and then pushing it somewhere, then what happens if their laptop gets stolen? What happens if they leave the company and they had like some special stuff on their machine that was how they built that model? So you're kind of left, you're kind of running out of options for like, well, where can we run this image build? I don't want to run it on my developers' local machines. I can't easily run it inside the development environment that my data scientists are using. And even if I did want to run kind of Docker from inside Kubernetes, then you have to do this thing that's called bind mounting the Docker socket. And this is a technique that gives security and compliance people like a big headache. And because it effectively gives every data scientist root on the machine that's running the cluster, and that's a very bad idea. So Google solved this with an open source project called Canico, and it happens to be the same open source software that powers their cloud build service. So they have a cloud builder as part of Google Cloud. And I won't go into all the details, but basically Canico just doesn't try and do the clever like overlay FS stuff that is kind of a performance optimization to make Docker work. Instead, it just, when it parses a run command in a Docker file, it just runs that command inside the container that it's already running in. And then at the end, it tars up the entire file system inside that container and sends that off to the container registry. So this Canico thing is like part of the solution here, it feels like. But Canico itself is a building block. And what you can do with Canico, and what we did with Canico in this project I'm going to share in a minute, is that we built a centralized service for image builds that run in a secure way on these multi-tenant Kubernetes clusters. So yeah, that's basically why you shouldn't try and build a container inside a container. So that's what this chassis project is that we worked on. It builds existing MLflow models into these container images. And it also exposes this Python SDK, which means that data scientists don't actually have to learn Docker. They can just use a Python API, basically. And the way that that works is that the data scientist will publish an MLflow model into chassis using chassis.ml.publish. So it works nicely with MLflow. And then that will make an API call to the chassis API server, which is this open source Python API server we developed. That starts a Canico job as a Kubernetes job, which builds the container with the model baked into it, which is the model itself is this diamond. And then is this a trapezoid? Anyway, the trapezoid is the container itself. And that container gets sent off to the container registry or can be pushed into the Modsy platform, and it will work in both of those contexts. So yeah, I would take you through a quick demo of that. And then I think we'll wrap up because we're going to run out of time. So I've got another one of these test drive setups. And in this case, we're not running Kubeflow and everything on here. It's just a Kubernetes cluster that has, I'll show you what's running inside this one. So it has the chassis service, sorry, which is that API server I just pointed out. It also has an object store implementation running on it. And it's also got KFServing, which is a system for deploying models into and actually running them in production. So I'm going to quickly show you that. Then, so basically, and you can try this demo yourself by running through the service demo notebook first, and then the KFServing.ipynb notebook second. And like I said, this is all available on chassis.ml. So yeah, in this service demo, I also need a Docker Hub account. So I'm just going to sign into my Docker Hub account quickly. And I'm going to copy and paste this because I need it later. So we're going to train a model. This is an MNIST model. And we're going to also wrap it. I can make this a bit bigger. We're going to wrap that model with some custom pre and post processing, which is a nice feature of MLflow that you can basically serialize some custom logic along with your actual model. You can then define a Conda environment. So this is a nice way of baking specific dependencies that you need, like PyTorch or whatever, OpenCV into your container image. And those dependencies will get installed when the model is built rather than kind of when the model starts up. So it gives you better reliability about making sure that those are working reliably. Then we can save the model into this MLflow PyFunc format, load in that model and test it. And then we can see we've got a bunch of files. We've got the pickle file, a conda YAML, and an ML model file that describes it. And then we are going to log into Docker Hub. Let me just fight with my password manager for a second. So I'm just going to put my Docker Hub password in here, because then the chassis service is going to build and push the model with that MLflow model that I just built and pushed into the MLflow registry. That exact MLflow model is going to get baked into a container image and automatically pushed to Docker Hub for me. So kind of from the data scientist's perspective, they didn't have to think about Docker. They didn't have to think about the server, the model server that they put in here. They can just go ahead and publish their MLflow models directly into Docker Hub, basically. So then I can show you what's happening. The chassis service that I described here is running this Kubernetes job, and the Kubernetes job is here. And so we can see what it's doing is it's installing all of those dependencies that I mentioned that are specified in the Conda environment. It's baking those into the container image. It's also baking in the model files themselves. And then it's going to go ahead and push that model into Docker Hub. And then the second part of the demo that I can do quite quickly, hopefully, is deploying that into KFServing. Now, I'll just find the tag. So that's the image that just got pushed by chassis into in there. And notice, by the way, that, yeah, chassis built that image in a multi-tenant Kubernetes cluster without causing a security headache. So you didn't have to think about that. And now we're just passing the image tag into this KFServing setup. We're not passing in a reference to downloading that image out of MLflow. And now I'm just quickly going to run some commands in here. That's going to keep going in the background. So we're going to deploy that model. You have to wait for the pod to get created. So that's creating the container. So what's happening there is that that's downloading the container from Docker Hub. That normally takes about 60 seconds. So yeah, any questions while we wait for this to ping over to ready?
There is one from a little bit further back. That was from Jess. General question, assuming our container is part of a larger system and its output is effectively our contract between other systems, how do you suggest testing and managing that contract so that other teams are comfortable integrating your model into a production system?
Yeah, I think that's a really good question. I think the answer is in the same way that you test any software. So there should probably be acceptance tests that deploy whatever the kind of candidate version of your software is, that test them against other components in your system. and you can take kind of a unit test approach. So yeah, basically acceptance testing is, and you should try and automate that as much as possible. So yeah, interesting. Okay, I think I lost the connection here, so I'm going to have to spin up a new one quickly. I'll just do the KFServing piece here. So sorry, I've got too many Jupyter notebooks up now.
Oh no.
Classic. So we're going to deploy that thing, and then we're going to go into the SSH for it. Oops, I ran that, didn't I? So now we're going to wait for that thing to start up. Okay, we're back where we were. Sorry, we're going to go a few minutes over today, I think. So yeah, it should take about 30 seconds to start up that container. So yeah, that's the container that automatically got built by the chassis service, got pushed to Docker Hub, and then we're deploying it into KFServing. Okay, there it is, it's running. And then we can get the host name out of it. Then we're going to download some data that we use to test the thing. And yay, we got predictions out of our production model. And so that was all done without the data scientists having to build a container image themselves. They just used that Python SDK. And so basically what I'm proposing here is that if you're an ML if you're a DevOps team that has an ML team in your company, then consider building a centralized service for model builds that you can provide as a service to your data scientists so that they can do the model builds themselves. This will make you very popular in your company, basically, because it means that basically it solves this problem of like, if the ML teams are the teams that have to build the container images, then it puts this onus on the ML teams to ship production-ready software and to have all of this DevOps knowledge that you might not necessarily want your ML teams to need to have. Whereas if you make the DevOps teams build the container images and like the ML teams email them the model files or something terrible like that, or Slack them to them, then this is going to slow down shipping models into production, because you're going to have multiple teams involved in shipping something, and that just means that the latency increases as soon as you add more people to a process. So consider creating this internal model building service that your data science teams can access via a Python SDK. Feel free to build on the work that we've done at chassis.ml, and that way the ML teams can build their own containers, but do so in a way that as a DevOps team, you can customize and control, and which are production ready. So yeah, that's the end of my talk. 6 minutes late.
I wouldn't expect any less from you.
Cheers, mate.
I just want to mention that people want to get involved in open source projects, and you do a lot of open source projects. You have open source basically in your blood. Mm-hmm. And so we have a few of those in the community as like basically community projects, almost. We could call them that. I haven't cleared that with you, but I would call them a community project, like the MLOps stacks. The chassis is a great one. The other one, box kite.
Yeah.
You've got all these different projects. And so if anybody wants to join you in creating cool stuff, we can make that happen. I would say reach out to you on Slack, right? And then they can figure out how to best be involved. And from that, I guess that's all.
Yeah.
If anyone else has any other questions, again, reach out to you on Slack, and we're going to finish it there. Luke, as always, man, it's a pleasure. I'm sad that we can't do this more. I used to chat with you once a week. Now it's more like once a quarter. But every time that we do talk, it is awesome. Really cool to hear your wisdom, what you got to say. I really thank you for this. And the voice coach paid off. You didn't say as much. So hopefully the YouTube comments do not eat you alive.
Well, kudos to you, because the truth is I didn't get a voice coach, but you were my voice coach just by saying that at the beginning. You made me think about it.
I guess we wouldn't even call it a voice coach. A voice coach is what I need for my singing in the beginning, and you, a speech coach is what they would call it. So anyway, that's it. I'm sure everybody is late to their next appointment. Thank you all for staying with us. Join some open source projects with Luke and the team, and we will see you later. Have a great week,
everyone.
everybody.
Bye.
Thanks, Luke.